Okay, let's try and see if we can investigate what the value e is. So what I've got here is the graph of y equals a to the x. And we're going to see what happens as I vary the value of a. So as you can see, that if we have 1 to the power x, we just get a straight line. We know that 1 to the power of anything is just 1. As we increase that, we start to see that 1 to increasingly high powers starts to climb quicker and quicker and quicker until eventually we get up to a is 2. And we can see that familiar pattern that we discussed previously. So 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, and so on. Similarly, 2 to the power of minus 1 just means the reciprocal of 2, 1 over 2, so we get a half. Minus 2 means 1 over 2 squared, so we get a quarter. And we can see that if we keep increasing that, it gets steeper and steeper and steeper and steeper and steeper. But the question is, what if we look at the gradient of that graph? So if we just type into GeoGebra f dash, because I've saved my original function as f, we can see that I get the gradient plotted here as well. And we can see that for values of a which are reasonably low, the gradient function is always slightly less than the gradient of the original function. Just remember, these are not y values. These would be the values of the gradient at that point. So it's telling us how steep is the tangent at this point. So if we look at this, if I take 3 for example, the value of 3 of the gradient at that point is 1.65. If I take a tangent directly above that, we should see that the tangent at that point has a gradient 1.65. So remember, the gradient function tells you the gradient of the tangent of the original graph at that point. So at x is 3, the height of this gradient function tells us the gradient of this tangent is 1.65. We can see that those two values are exactly the same. If I was to move a along to 4 and b along to 4 also, you can see that I've not quite lined them up perfectly there, but they should be exactly the same value again. So let's just get rid of those points. Okay, so the blue function is our gradient function. The reddy brown function is our original y equals a to the x. So it appears that our gradient function is always below our original function. But we can see that as I increase a, it starts to get very, very close to it. Until eventually I reach some special value where the two graphs exactly overlap. It appears they exactly overlap. If I zoom in a lot more, we can see there is still a little bit of daylight in between them. So maybe I just need to increase a little bit more. And we can see that if I zoom in, I'm very, very close now. I really need to zoom in a long way to start seeing some daylight. But then if I increase it one more bit, it flips the other way. So if we just reset our axes, there we go. So somewhere around here it appears that the gradient function is exactly equal to the original function. If I go too high, the gradient function increases quicker than the original function. Go too low, and it always increases slower than the original function. So we're going to be interested in this special value here, somewhere in between 2.71, 2.72. We call this special number Euler's number, or E for short. It has some fantastic properties that we'll meet as we learn some more maths, but for now we're just going to be looking at the graph y equals e to the power x. And E, Euler's number, is just that very special number. So you see, if I remove those, leave myself to just this orange graph, we get g of x is e to the power x, e being that special function where the gradient of the function is the same as the value of the function at that point. So if I now plot g dash, you see the purple function exactly overlays the orange one. Doesn't matter even if I go to some very, very extremely high values. Let's just pull this in a little bit. Let's go to some very high values. I never see a gap appear between the two. Even if I zoom right in on it, I should never ever see a gap. Because I'm using the exact value of e, the gradient is always exactly the same as the value of the original function. Never any daylight between them. E is one of those numbers like pi, an infinite decimal, just keeps going, so we'll just kind of know it's somewhere around 2.7, that's close enough. Okay, and we'll use this number in the abstract. It comes up a lot next year when we're doing calculus. Thank you.